Hey everybody, it's Mr. Francis, and this is the quick review for Chapter 12, which is focusing on bonding. Okay, so Chapter 11, as we looked at the elements, one of the things we talked about was the arrangement of the electrons, and we talked about valence electrons, those electrons that are in the outermost energy level. Those valence electrons are going to play a big role in what's holding atoms together, and that's these bonds that we have. And then you can see the definition for bond and also for bond energy. Okay, much like there was two types of compounds, there are two types of bonding. What we call ionic bonding, and again, look what we said, the ionic bonding exists between the ionic compounds, those that have the metals and the nonmetals. And the key here, the electrons are transferred. The metal loses the electrons, the nonmetals gain the electrons. There's the transfer. The attraction, then the ionic bond, is that attraction between the positive and the negative charge. Covalent bonding, instead of a transfer, now it's a sharing of the electrons. And the key here now with the sharing, ionic bonds were with metals and nonmetals. Covalent bonds are going to be with just the nonmetals. So these are going to be the ones that we see in the molecular compounds. And again, it's the sharing of the electrons that we see for that. Now, with those covalent bonds, that sharing is quote unquote. Sometimes the sharing can be unequal, sometimes the sharing can be equal. And that's where you're going to see between what we call polar covalent bonds and non-polar covalent bonds. And again, what happens is with a polar covalent, we get this unequal sharing of the electrons. That unequal sharing comes about because of a property known as electronegativity. And again, you can see the definition of each one. The next slide is going to have a periodic table with electronegativity values. And one of the things that you'll see is our nonmetals over on the right side of the table have the higher electronegativity values. The metals tend to have very low electronegativity values. And again, think about what the definition is. The ability of an atom to attract electrons to itself. So what that's saying is that the metals tend not to attract electrons to themselves. They'd actually like to lose electrons. Where the nonmetals, hey, they're all for sharing the electrons and getting, and being able to attract them to themselves. And what you can do, those numbers, you can look at this table. As you look at this figure, you'll see the electron negativity for each of the elements. The higher the electronegativity, the more attraction it has for the pairs of electrons. We talked about atomic radius. We talk about ionic radius. And what we tend to see with ionic radius is, we saw this in the last chapter, cations tend to be much smaller than the metals they came from because of the loss of electrons. Anions tend to be much larger than the nonmetals they came from because of the additional electrons. And that's what you see in the answers for this one. And for here also. So the sharing of the electron is going to be based on, as it says here, the difference in the electronegativity values. And quite simply, go back to that figure 12.3, just subtract the two atoms. The more electronegative ion, the more electronegative it is, between the two atoms, the more unequal sharing we're going to see for that. And I like this table 12.1. Because it kind of gives you an idea in terms of the bond type, the electronegativity difference, and the character of the bonds with this. Again, from most polar to least polar, just do the math. Go back to figure 12.3, subtract the values for each one of these, and then you'll be able to solve for your answer. A dipole moment, because of that unequal sharing, what you tend to see is that the more electronegative atom tends to have a negative charge to it, a partial negative. The lesser electronegative atom is going to be more positive in nature. And that's one of the things with water. Interesting thing, if you get a chance, take a magnet, get a small stream of water, run the magnet by that stream of water. Depending on what pole you're holding, you're going to see something very interesting that water stream is going to do. And I'll let you guys do that on your own. Just some review for configurations and the types of cations and the charges. We saw all of this in chapter 10, or chapter 11, excuse me. The reason for the gain or loss of electrons is everyone wants to get this noble gas configuration. And remember from chapter 11, the noble gas configuration is one where they have the full outer valence shell, S2P6, regardless of the energy level that we see with it. So metals, when they lose their electrons, in doing so, they get that noble gas configuration. The nonmetals, when they gain electrons, they're going to get a noble gas configuration. And again, you see here's table 12.2, and you get an example of the electrons that are lost, the electrons that are gained, and the corresponding electron configuration. Again, the neon here, that's the configuration for the neon atom. For ions, as I said, I like this statement. But here's the key. It's not just any electrons that the atoms are going to lose. It's the valence electrons. It's those outermost energy level electrons that are going to be lost by the atom, by the metal, or gained by the non-metal for this. And again, these next slides kind of show what's going on. Again, with a covalent bond, they're sharing, but it's still the valence electrons that are being shared between the two atoms. Again, this is going into charges. One of the things we talked about, if you remember, for charges, the ions within the same group have the same charge of the ion. And that's what you see here in table 12.3. The attraction in ionic compounds are very strong. It's a plus or minus, but it's not just two atoms. Remember, you've got, in an ionic compound, you've got a multitude of cations and anions that are held together. So they tend to be very strong, tend to have very strong properties. This gives you an idea. Here's lithium fluoride, and you can see the arrangement of the lithium ions, the fluoride ions. Yeah, the formula is just LiF, but note multiple fluorides, multiple lithium ions that we see here. Again, this is something we saw in the last chapter. Cations are always smaller than the metals they came from. The anions are always larger than the nonmetals that they come from. Polyatomics, much the same way. We mentioned briefly Lewis structure. And again, a Lewis structure focused on the valence electrons for the particular atoms. And we use those Lewis symbols to show this sharing. When we write a Lewis structure, two things, bonding pair and an unshared or a lone pair. And those are two terms that I want you to take with you as you're reviewing through this chapter. When we write a Lewis structure, always follow the steps. Add up the number of valence electrons. We saw in chapter 11 how you could figure out the number of electrons for a particular atom. And I like the next steps. You're going to have a central atom, so one pair of electrons from the central atom to each of the outer atoms, and then give any remaining electrons to the outer atoms itself. So here's water. So when we look at the structure H2O, note the arrangement here. It's not lined up hydrogen, hydrogen, oxygen. You've got this central oxygen, and there's the electron pair to each hydrogen. Okay, so in a Lewis structure, you're always going to have a central atom and you're going to have your outer atoms. Typically, your central atom is going to be the first element in the formula, unless it's hydrogen. If it is hydrogen, then the next element in the formula is going to be your central atom. Here's an example, phosphorus tribromide, PBr3. Look at the structure. Again, phosphorus is the first element in the formula, so it's going to be the central atom, and then you have the bonds to each of the three bromines. And note they're not lined up bromine, bromine, bromine again. There's a bromine, one bromine is bonded to the phosphorus. And you get the structure for, and again, here's CO2, carbon dioxide. Note, first element in the formula, hey, that's my central atom. The two oxygens are bonded to that. There are some exceptions. Again, we always want that noble gas configuration so we can have fewer than 8 electrons. And these are just some concept checks that you can read through with it. The last part of the chapter, now that we have the structure, there's a three-dimensionality to these molecules. This is the first one here. This is carbon dioxide. This is the boron trifluoride. This is methane CH4. How we draw them and how they look in three dimensions are two totally different things. We've got three sets of structures. There are what we call a linear structure, a trigonal planar structure, and a tetrahedral structure. And each of these structures come about because of the arrangement of the atoms in the formula and how we have that. That structure is based on an idea known as VSEPR, valence shell electron pair repulsion theory. And I like this statement here. The structure around the given atom is determined by minimizing repulsions between the electron pairs. We want to get the electron pairs as far apart from each other as possible. So if you have two pairs of electrons, the farther apart you can get them, 180 degrees. If we have three pairs of electrons in that central atom, the farthest we can get them, 120 degrees. There's that trigonal planar. And with four electron pairs, instead of looking like a square, it's actually a tetrahedral. You got 109.5 degrees in the angle. And you're going to be asked, and you're going to see this on the quizzes in the exam, to draw a model based on VSEPR and identify the things. Follow these steps. Just go through them each way. And then you can put that together. And I like this table, table 12.4. This is a table that I want you to reference when you're putting together the molecules and you're asked to identify the structures for that. And double bond, if you got multiple bonds here, look what they're saying here. The double bond is counted as a single pair with that. Okay, just a quick review. So if you have any questions, feel free to contact me. Keep up the good work. Talk to you soon.